Hello everyone, thank you for coming out this afternoon. Let me start by mentioning two upcoming events. We're near the end of term, but we actually have two lectures coming up within the next 2 weeks. So Thursday, April 10th at 7 p.m. in this room, Joel Lexgen will be speaking on Those Who Have the Gold Make the Evidence, the Pharmaceutical Industry and Clinical Trials. That's a talk that's from 7 p.m. to 8:30, and it's co-sponsored by the Situating Science Cluster. So I hope that you will consider coming out. It looks like a really interesting talk. We also have an upcoming talk Monday, April the 14th in the Rotman Speaker Series. It's at an unusual time. It's at 11 a.m. to 12:30. It's Charlotte Berndl, who is at the LSE, although she's just now moving to Salzburg, who will be speaking on confirmation and calibration in climate science. So we hope that you'll be able to make it to that talk as well. So it's a real honor to introduce Bas van Fraassen to give his second talk as this year's Rotman Lecturer. Professor van Fraassen's work has shaped philosophy of science over the last 35 years, and his interests and contributions span an astonishing breadth of topics. He is one of the few among us who truly pursues philosophy as it was characterized by his mentor, Wilfrid Sellars. The aim of, quoting Sellars, the aim of philosophy, abstractly formulated, is to understand how things in the broadest possible sense of the term hang together in the broadest possible sense of the term. And I think he can claim to achieve what Sellars regarded as success in this endeavor, namely to know one's way around with respect to all these things, in that reflective way, which means that no intellectual holds are barred, by which Sellars meant requiring a thorough knowledge of the subject matters of a variety of special disciplines. And we all in philosophy of science have benefited enormously from Professor van Fraassen's insights and contributions he has developed in coming to know his way around in Sellars' sense. Professor van Fraassen's work is characterized by a striking generosity of spirit. There are at least 3 books, and I'm worried that I'm missing a few here, that are devoted to critical reflections on his work, which include his replies to his critics. These replies exemplify constructive philosophical engagement, displaying equal parts tenacity and grace. And van Fraassen seems to seek out such opportunities to hone and develop his positions through confronting his critics and challenging discussions. So it's exciting to have Professor van Fraassen speaking to us today on a topic that's been a central focus of his work, the semantic approach to scientific theories. In large part due to his influence, this approach has by now become conventional wisdom among philosophers of science. No one's better suited to review the development of this approach and the potential for further contributions than Professor van Fraassen. So please join me in welcoming him to speak about the semantic approach.
I'm very happy to be here. Thank you for inviting me. The last day and a half, I've been nostalgically reminiscing about times here at the University of Western Ontario. And in the 70s, I used to spend a lot of time here. And some of the things that I'll talk about certainly were developments in that time closely connected with what was happening here. And there are even some other people here, almost as old as me, who remember this, like Bill Harper, right? Okay, so just to begin, my initial focus will be on some years that's around 1968. Was a very revolutionary period in many ways. There was a spirit of rebellion and revolt in many areas, and certainly also in philosophy. The philosophy of science was still dominated by a view that Hilary Putnam called the received view. It's the view of scientific theories that was part and parcel of logical positivism. And of course, when he called it the received view, it was because he was critical of it, right? I mean, that's how you begin your criticism. I'm the underdog, right? This was we wanted to reject this view and replace it by something new. Another rebellion going on, in this case, in philosophy of science. I'll talk a bit about the prehistory, about what happened right around that time, and in the end I want to raise questions about what about an aftermath? What about what is coming? I mean, at that time, the received view, the logical positivist tradition, was 50 years old. well, at 50 it had to die. Right? Now, the semantic view is at least 50 years old. And so it's clearly, a time for renewal. Okay. It's hard for me to date things precisely, and I certainly shouldn't try to do that. Let me first say what is the received view, then what the kind of objections we had, so that we felt it had to be replaced, and then what the semantic view proposed instead. Okay, so the received view of scientific theories, it begins with a real debt to Hilbert's work in Foundations of Geometry. That is a language which is presented as uninterpreted. It's the pure mathematical part of the scientific theory. But, well, it's not supposed to be a purely mathematical theory, so, according to the positivists, its vocabulary has an important demarcation between what they call observation terms and theoretical terms. And then it's a scientific theory, I mean, scientific in the sense of the natural and social sciences, so there has to be an empirical part, right? There has to be an empirical connection. And this, they said, consists in correspondence rules that connects the observation vocabulary with humanly possible observations and operations, and of course measurement results to be more specific. What meaning the theoretical terms have, they will have to get indirectly through this connection between observation terms and observations and manipulations. Right? But that was the picture of what the scientific theory is like. And you can see that, I mentioned Hilbert, you can see that because it begins by saying, here's the language and the theory, it was very much in tune with the kind of logical developments at the time that were the inspiration for logical positivism. Okay, so now, according to Fred Suppi, there's a very specific date when it died. 1,200 persons were in the audience, and at the Illinois Symposium on the Structural Scientific Theories, which Fred Suppi had organized. And then I think, Chris already said some nice things about the semantic view. I don't have to sing the praises, because the critics also do that, like Hans Halvorsen, who is a prominent critic, who says within a few decades, the semantic view was the new orthodoxy. And, I have some anecdotal. For instance, at PSA, there was a talk by Tom Kuhn, who said, I didn't know what the semantic view was until Lisa Lloyd explained it to me, and then I felt like that character in Moliere, who realized he'd been speaking prose all his life. So, it certainly was a view which I hope you'll see. It's rather closely connected with what actually happens in the sciences, whereas one thing that we didn't like about the received view is how far it had gone toward logic as opposed to science. Right? This is not a bad thing in itself, but it was a bit far. Now, what exactly was rejected in this? Suppi published the proceedings of the conference. If you look just at the papers in the conference, not easy to see exactly this death and birth, okay? But it was published in '74, and the very long introduction by Suppi himself explains it very well, and I think actually it is quite accurate, though it has to bring out things that were going on as opposed to what was said. And Toulmin wrote a postscript in which he tries to explain exactly what was his received view and what was being rejected. And I'll just quote a little bit from it. The logical positivism was closely connected with the unified science movement. And the idea was that they would work on the construction, the Aufbau, right, of a language that the whole of science can be developed in. So that science would be unified by being all developed in one, all the theories would be in one language, right? So they hoped to do what Peano and Russell apparently, or they thought, had done for logic and mathematics. But of course they would have to add special primitive terms to make connections with the observable, well, it was a kind of ideal of Mathesis Universalis, of the sort that Leibniz had. Well, okay, what could be wrong with that? I mean, why isn't it, wasn't it a very good and laudable project? Sure. But still, we had some real misgivings about it, and especially about the way it was carried out. Two objections, especially, maybe I should say two critical questions, right? The first is the question, well, what kind of value does this enterprise of logical reconstruction have for gaining an insight in what the sciences are like? Because the sciences, after all, is what we are supposed to be looking at. And secondly, going a bit farther, what kind of presuppositions are driving this particular way of reconstructing the reconstruction of science? So, about the first question, of course, we ask the question in that particular way because, it's a rhetorical question to some extent. Not much insight is being gained, that's the idea, right? So, I mean, here's an example. I'm just quoting a line from a quantum textbook, quantum mechanics textbook. Attributes of the system are represented by Hermitian operators. Can this be formalized in first-order language? Right? You can give it as an exercise to your first course students, right? And they'll do it, right? For all x, if x is an attribute of the system, blah, blah, blah. But if you look in the physics text, the exercise that comes with that line is rather different. The physics student knows the general idea, the general concept of a harmonic oscillator, and says, oh, I have to interpret this P and Q, the position and momentum, as being represented by Hermitian operators. So if I'm supposed to find the energy level, I have to solve that equation. And what does he find? Discrete energy levels, no zero level, etc. Well, the physics student isn't learning any logic, but the logic student isn't learning any physics, right? So we thought, well, maybe the exercise we should give to the philosopher is find some places where it could be useful to use these formal methods, right? And not that we're not convinced of the value of formal methods, but let's find places where it actually does something for us. Okay. The other thing that I think I should definitely mention, because Kuhlmann, although he was one of the people involved, does not emphasize this. There was something really important about the presuppositions of the logical positivist enterprise that was rejected already by that time in our cohort. Okay, the critique of logical positivism by Feyerabend, Maxwell, Sellers, Kuhn, Hansen had already completely taken hold. Now, we knew some of these people. Sellers was my teacher. Hansen was my colleague at Yale, my first job. But even the ones we knew were heroes. Okay, I mean, heroes in the philosophical firmament, larger than life. Right? Every single one of them, and partly because they had convinced us so strongly to see the language of science in a very different way. Not in the way the logical positivists had seen it, as needing radical interpretation. Okay? I think that the positivists, because they start with Hilbert's idea that you have to begin with an uninterpreted syntax, treating this scientific language as in itself unintelligible and having to be given meaning. And that's why they had to introduce the correspondence rules and try to find some indirect ways to get meaning. But the new light was, no, scientific theories are being presented in natural language that we understand. It's not a question of interpretation or reinterpretation. The theory, to understand it, you have to take it literally. Okay? So, just as a slogan, if a theory says there are electrons, then it's true only if there are electrons. Now, this is a bit of stonewalling against logical positivists, but I think you see what is meant here. Theory is involved in the concepts that are expressed in natural language, absolutely. But there's no sort of demarcation or sort of limit that says theoretical, not theoretical, right? We have to deal with language as it is, but we understand it. Now, as David Lewis at one point said, and I think this is very apt, I say understand and not say I can analyze. It's not the same thing, right? But now there may be some words, of course, and scientific words that are not already part of our family. If yesterday night a string theorist introduced a new term, nobody knows it yet. The theory, whatever theoretical development he's proposing hasn't taken off yet. Yeah, that's not part of the linguistic family yet, sure, okay? But that's not the sort of term that's appearing in the philosophical debates. It's terms like molecule, electron, that's already like 100 or so years old. So this is really a really important part, that we reject this theory observation language distinction. We take language science to have to be understood literally, not reinterpreted. That doesn't mean there's no role left for interpretation. I mean, think about what happens in the English department or comparative literature department. Maybe they are reading a text like Milton's Paradise Lost. It's all written in English, natural language, a language you understand, but there's certainly a lot of interpretation going on, and it's a call for interpretation. And in the case of the sciences, that's true too. There's a role for interpretation, or several roles. First of all, even if you understand, so I say the scientific text, you may not yet understand it to the point that you have no puzzles. You may not yet understand how the world could be the way this new theory or strange theory or even familiar theory says it is, right? So that is a call for interpretation. And you know, probably in the case of quantum mechanics, that's the most salient kind of example. And secondly, we said there is despite the fact that the language is understood, there is certainly a role for semantic analysis of the language. But we have to restrict it to the part of the language that's going to help us in understanding the science. So what is meant by semantic analysis here? Well, you know, it's not as if we were throwing away all the logical tools and concepts that the logical positivists have introduced into philosophy of science. No. No, we really understood the value of that, okay, and insisted on it. So this idea of semantic analysis had begun in logic in the 30s by Tarski as a different approach from the earlier axiomatic syntactic approach to theories. But he begins with an idea that's very familiar in the sciences. The first sort of example of a sentence is an equation. And what's important about an equation is not so much its form as the set of solutions of the equation. And what is the solution of the equation? Well, it is mathematical objects that satisfy the equation. So if you have several variables, you will have a little sequence of objects that you say, here's a solution, there's a solution. So a very simple example of an equation, 3x squared plus 4y is 7. The pair minus 1, 1 is a solution, because if you said x equals minus 1 and y equals plus 1, then the equation is true, right? And similarly for 3 and minus 5. And so Tarski generalizes that. He talks about a general form of language in which there are 3 variables, and he says an open sentence is one that has 3 variables in it, and is satisfied by sequences of objects in the domain that the language is about. And this is step 1 in his construction of models for languages, and his new conception of truth, or his logical conception of truth. Okay. These are the tools that Carnap could only come to very lately and tried to keep in this sort of syntactic form that we wanted to go to immediately. And you know, this is partly because at that time, I mean, I'm talking about around 1968, 1970, big news in philosophy was the semantic analysis of modal logic. Okay. Modal logic had been a disputed area where people were trying to look at different principles, saying what would be right and so on. Came along semantic analysis and was solving all these problems. So Kripke, Kanger, Hintica, Montague, Kaplan, Dana Scott, you know, these people were making big news in philosophy at the time. And so we were saying, yeah, this is wonderful. let's see how we can adapt semantic analysis to the language of science. Now, I'm talking as if, we're doing everything new. That's not true, of course. I mean, we are pygmies standing on the shoulders of giants. Who said that? I don't know. Wasn't it Newton, Bill?
Yes.
I think anything great I quote, he's going to say, yes, Newton said it, right? Okay.
If I could see further, it was because I was
Right. So, the kind of semantic analysis of language of science that we were proposing, it was first proposed, but not under that name, of course, in the 30s when John von Neumann was writing about foundations of quantum mechanics. And he was talking about how the basic form of sentence to look at, basic form of equation, just this, this quantity has that value, or the quantity has a value in that interval, right? And a sentence like that, it's true of a system, say a quantum mechanical system or another mechanical system, exactly if the state of that system is in a certain region of its possible states, its state space. So every sentence of that sort has as a semantic value a region in the state space. And logical relations among these sentences, they have to come from relations among these parts of the state space of the theory. The state space being made up of the models of the theory. And with Birkhoff, he wrote a joint article in 1936 that now is very famous. But this stuff didn't get much attention among philosophers. The first philosophical publication that I found about this was by a philosophical physicist, Hermann Weyl. In 1938, he wrote this paper called The Ghost of Modality. Now, philosophers didn't have much access to it. He wrote it in 1938. It was published in 1940, when the Second World War had just begun, and it was in a festschrift for Edmund Husserl, which analytic philosophers don't tend to read, right? But it's a wonderful article. It's about intuitionistic logic, modal logic, quantum logic, about the semantic analysis of all these. He still midstream. He has lots of problems, especially with modal logic. Okay, problems that he brings up, and he doesn't trust it very much. But when you look at what he is saying about the semantic analysis of such languages, it's exactly following the Birkhoff von Neumann, which became, of course, very well known later on among philosophers. But at the time, the next publication that I know of where this appears is just after the war in a little philosophy of science textbook in Dutch by Evert Bed, who wrote the textbook during the war along the lines that he was following Carnap. And then when it's about time that it can actually get published a couple of years later, when there's paper again, etc., he puts in a little postscript saying, yeah, well, I was wrong to do it that way. The way to do it really is like Birkhoff von Neumann in fact. With Hilbert space, he says. So, and then in 1948, he publishes 2 articles to quickly outline that to the philosophical public that he gives at conferences. But people didn't really notice much. Okay? It took a little while longer, right? But this is one of the precedents for it, and it is something that we followed by that time. The way you have to think about this language then, first of all, it is tailored to a specific theory. The terms are the quantities that this theory is about, so to speak. The quantities that appear in the models of that theory, right? And what I'll call the elementary statements, they all have the same form. Quantity M has value in E. Right? You can introduce things like and or and not, but if you do that, they have to come from the relations among the semantic values. In other words, among the corresponding regions of state space. So, for instance, the conjunction of M has a value in 0 to 3. It also has a value inside 2 to 4, interval 2 to 4. Well, that means this value is inside the interval 2 to 3. So it's all right to have a conjunction, but only because it can be equivalent to an elementary statement. Now, if you try to do that with OR, then it's going to depend a lot on the theory that you're looking at. It's not going to be the same in different theories. You can also have basic principles expressed simply in this form. I mean, F equals ma is always 0. It's the same as saying F minus ma is 0, same as F equals ma, right? Why did we think that this would be a better thing than what we had? Well, you have to think about what we were looking at. There were two programs developing that use formal methods, but in very different ways. Montague was, so to speak, motorizing the received view. He was developing a large-scale intentional logic and discussing scientific theories as sets of sentences in the language of intentional logic, and applying, the sort of methods that Condap had applied, but at a much more sophisticated level. So one extreme, it is really, the received view made more formal. We had some specific objections to it, but partly it was too extreme because it takes in too much so that you lose contact with trying to find out exactly what the science is doing, right? The other program was opposite in the sense that it wanted to discard any discussion of language. That was Patrick Soupis and his group, who were developing a way of presenting theories in terms of sets of models as set theoretic structures, and saying, just forget about the relation with language. And this also was not satisfactory because there were so many problems in philosophy of science that did seem to deal with language. So we wanted to say, don't just banish the attention to language, but rather restrict it to the specific language used to describe the models. So we thought of it as perhaps a golden mean between two extremes, and wanted to see if this could be fruitful. Well, it was fruitful partly. It got an impulse from what was happening in foundations of physics at the time, because in foundations of quantum mechanics, the attention to quantum logic had come in new after the war, especially from French physicists like Piron, Swiss like Jauch, and it was, well, there were great conferences right here in Western Ontario where this was developed, and of course Jeff Boop, who was here, was one of the major players in it, and so was Bill Demopoulos, and Cliff Hooker was working on it, and myself and Rick Hughes in Toronto were working on it. So, this was a development that was closely connected with Western Ontario as well. And it was at the conferences here that I first met the European colleagues, physicists and philosophers and mathematicians who were working on that. And then, of course, there were many more conferences of that sort over there. I'll just give a few ideas to give you some of the flavor. The view of language in some way was rather traditional. Traditionally, the distinction is made between the intension of the words and the extension being the relation to things in the world. And so the way we construed that was the intentions of the words, well, that's the semantic value inside the models. When you say, like, the term position refers to that Hermitian operator in the model, okay? But then there's a connection between the models and the phenomena when you say, oh, this phenomenon fits into this model in the following way. So extension for the terms comes in an indirect way, only when the models are representing certain real phenomena. Otherwise, they don't have an extension, but it doesn't matter because the logic comes entirely from the intentions. So this development, so then quantum logic is developed along those lines, that you connect regions in the state space with the sentences that give their truth conditions and so forth and so forth. and you have to, you're well away into non-Boolean logics when you are there. All right. So much now for the initial development. I won't take our time twice for a little polemical interlude because, and both of these are responses to fairly recent criticism of the semantic approach. I mean, there were prior criticisms too, like by Roland Prigg and so on, but I want to take up just two here. Hans Halvorsen wrote a paper published in Philosophy of Science a couple of years ago called What Scientific Theories Are Not. And what he was arguing was the semantic view is just wrong. Okay? I've written a reply to it, and it's already accessible because Philosophy of Science has started putting accepted papers on their website right away. So if you look at the Philosophy of Science website, you can find my reply. So I'm not going to do a lot of criticism here because you can go and read that if you want. But I can very quickly show you how Hans Halvorsen is talking about semantic view as it would have looked to someone who was brought up in the received view and thought it had to be like that. Okay, so he says the semantic view says that to present the theory is to present a class of models. So the model, you know, if you're going to identify a theory, you have to say this is a set of models. But he says that's certainly the wrong view of the theory. And he starts giving an argument. Now, to begin, I think you can see from the quotation that he's immediately thinking of it in the way that the received view thinks of theories, right? The models of sets of sentences in a particular first order language, right? So he says, please grant me that. And then he argues that if you try to formulate criteria of equivalence between theories that refer to the members of this class of models, with no reference to their connection of language to language, then that does not correspond in any way to what we normally take to be definition equivalents of first-order theories. I think you can see just from the language and so on that, you know, this is somebody in the received view saying, what does the semantic view look like in my framework and why doesn't it work, right? The relation between the models and the phenomena that we call representing the phenomena is simply totally left out of account here. And in the footnote he says, I'll just leave it out of account, right? But in that case, you know, identity criteria are just, you know, looking at a part of the theory. Okay, so that is basically the criticism. But, you know, some really important things come out in his article. And also he has a program for developing something that is much closer to, say, Montague or Carnap, and that he's going to develop at the next PSA, present the development of the next PSA, and that looks in its own way fascinating. Now, I'm not saying that it is a, you know, I'll have to wait. I doubt that it's going to be a good rival to the semantic view, but okay. But there are some things that come out already in his paper that I think are really interesting to note, and that are right. He says, these are not, you cannot get a good notion of equivalence of theories. Why not? Because you can have the same set of models and have two different theories, or you can have the same theory and two different sets of models when you present it. Okay, fine. Well, you see, I think that is not only, that's not a criticism, because I think it's exactly right. Because at least right as I would interpret those statements. I mean, here's an example. You know, many of you recognize this this equation, the diffusion equation. Right? Now, this can be offered when you're modeling a gas diffusion. It can also be offered when you are modeling diffusion of heat in a substance. Two different theories. One is about gas, the other one is about heat. Same mathematics, right? So the same set of mathematical structures. Yeah, but it's two different theories. Why? Because these mathematical structures are being used to represent very different phenomena. What the theory is of is not the same in these cases, even though what it presents the thing as being as is the same, right? It's an important thing to know about theories, that that's a possibility. Also, the other side, can we have different sets of models that present the same theory? Well, I think there's a nice example of that. Early in the 20th century, some people were really into axiomatizing classical mechanics, especially, first of all, classical particle mechanics, and then like Ernie Adams working on continuum mechanics. Well, you see, when you are formalizing, when you are axiomatizing, there's going to be places where you have choices. But from the point of view of the empirical content of the theory, they don't care. So, in classical mechanics, in practically every situation you can think of, if you get the kinematic data, the movements of the bodies over a period of time, you can deduce the masses and forces relative to Newton's theory. But there are cases where you cannot. I mean, the simplest case would be you have one particle, it's moving in a straight line, it's never accelerated. What's its mass? Well, you can't tell from that, right? So, in the axiomatic versions of the theory, different people make different choices. Mackey just said, assign them all a standard value, because they don't care anyway. Some say, no, I'm sure Newton thought that everything had a mass, whether you could tell or not, so it could be an arbitrary value. That's a matter of fact in nature, what mass it has. And the third one, like Herbert Simon said, look, let's let the mass function be just a partial function, partially defined, not defined in cases like that. These are not three different theories. In each case, if you know what model one would present, the other, you know what the other ones would do, right? They only differ in things that Newton would not have bothered his head about, right? So, yeah, one theory, three different sets of models. It's true what Hans Halvorsen said, that the identity criterion for a theory cannot be the set of structures that satisfy the equations. That's absolutely true. But it's nice to think about how the same mathematics can be used to represent different things, and also how mathematically different presentations could really amount to the same scientific theory. Okay. So, I love this criticism because I think it's right, but it's good. Okay. End of the first polemical interlude. What Hans Halvorsen would definitely not be very satisfied with here is that Carnap and Montague and Halvorsen, they have very precise, direct answers to the question, what is a theory? And the semantic view doesn't. The semantic view says things like, if you present the theory, if you want to present the theory, you'll have to present a set of models to represent the phenomena. Oh, that's pretty informal, right? But what kind of answer, what do we need from an answer about what is a theory? Well, whatever we say a theory is, it should be the sort of thing that you could believe, or disbelieve, or doubt, or contemplate, right? It should be something that gives information, whether true or false, about what things are like. And if it consists in offering models, well then it can only do that if these models are offered to represent how things are. Okay? So if you're identifying a theory, you have to do these two things. You have to say, what is it of, and what do the models represent it as? So, for example, the wave theory of light represents light as a wave motion in the material medium. So I'm saying it's of light, and it's as a wave, right? The kinetic theory of heat represents gases, that's what it's of. It represents them as an ensemble of molecules, that's the representation as. Now, there is nothing formalized here. And that's why I think it's not precise enough to the taste of someone like Montague or Hans Halvorsen. But to my mind, it's enough. It's enough as an answer to what the theory is. Okay. All right. So now, to continue a bit, I want to give a less technical but a more general example of how within the semantic view we were trying to tackle traditional problems in philosophy of science, trying to see if we could come up with some good answers to questions that people were concerned about. And in the early 70s, around 1970, 72, several philosophers had written articles to say that the distinction between truth and empirical adequacy of a theory is a distinction that can be maintained. There can be no such distinction that you can draw a line like that. So also, if you ask whether two theories are empirically equivalent, it ends up making no sense at all unless you mean completely equivalent. Okay? And they had the reasons that Richard Boyd and Michael Gardner gave were things like this. When it comes to observational consequences, which is supposed to be what's right, to have empirical adequacy, you can't really tease out observational consequences without auxiliary hypotheses about what the substances are like, what the instruments are like, and so on and so forth. Okay? So, just the theory by itself does not identify the set of observational consequences that are relevant. Well, how are we going to do that? If you just let anything be an auxiliary hypothesis, then it follows very trivially that observational consequence and consequence are no different anymore. Okay? If you say, well, no, we will have to restrict the class of auxiliary hypotheses, they say that turns out to be a totally intractable problem. Michael Gardner says it's like the problem that Goodman had when he tried to say in a counterfactual conditional, what are the relevant things to keep fixed for your antecedent, which, of course, at the time was a paradigm example of an intractable problem, right? There would, you can see also the way that the question was posed by them. It's within the received view. They're talking about observational consequences, meaning sentences that are abusable and whose terms are observational vocabulary, right? There would have been a cheap solution for them. They said you have to add new primitives to your language in order to represent the scientific theory. So why didn't they just add the word observable? Right? Well, nobody proposed that, nobody tried that, and I don't think anybody would have liked it. And probably this was in part because of Grover Maxwell's famous paper that says you can, within the language, draw a distinction between observational term and non-observational term. Now, we all agreed with that conclusion, but more because of Feyerabend and Kuhn than because of Maxwell. Because Maxwell's arguments, I don't think were very good. He gives slippery slope arguments, and slippery slope arguments, are not great. My favorite example is Sextus Empiricus, who argues, or who presents the argument that incest is not immoral, because look, touching your mother's big toe is not immoral, and everything else is a matter of degree. Okay? That's a good slippery slope argument. Now, the other argument that Maxwell had is that maybe at the moment some things aren't observable, but if we were to evolve into organisms with something like electron microscope eyes, then they would be observable. So it's clearly the case that these things could be observable, and then from could be observable, he infers they are observable. Now, nobody would make that inference in some other cases. I could be fat. Doesn't follow I am fat, right? But even about Hubble, this could be a portable desk if we were to evolve into giants. This could be a portable building. If we all developed into huge giants, the human race became giant, but that doesn't mean it is portable, right? So I don't know why, but Maxwell's conclusions were right. So okay, then you can overrule a lot of things. Okay. Anyway, Boyd and Gardner may be right about not being able to draw the distinction in this view. But the problem is not going to go away, because the question of how measurement results, which is observation results, right, are related to the theoretical models, is definitely a problem that has to be addressed, one way or another. Okay? So if the problem is not going to go away, we have to find some other approach to it. And that started with Patrick Soubise, who started talking about hierarchy of models. There are the theoretical models at the top, and at the very bottom there's the data model that you make up from the experiment. And he says, you know, the results of the experiment have to go through a conceptual design so that you actually get to a small model that then you have to confront to the theoretical models. And you have to see whether this data model can actually fit into, isomorphically he says, into one of the theoretical models. Right? So this was the form of solution that he offered. And I was very much taken by that. I thought, yeah, that's exactly how we would put it within the semantic view as well. His examples, you know, he was working on experimental psychology, so his examples were from learning theory. My favorite example was to think about the moment when the Newtonians or Newton is confronting the Cartesians and saying, look, kinematics is not enough. Doing your physics just in terms of length and times is not enough. We have to introduce terms like mass and force. And absolute space and absolute motion and all the things that you want to introduce in order to make sense of the world. So he refers to the apparent motions, which is the motions that you can describe just in terms of length and time as you observe them. And these are the kinematic structures. They have to somehow be properly related to the real phenomena, which means be able to fit into a Newtonian model. Right? So I thought this is a great form for the solution for this question of what is empirical adequacy, and that it would maintain the distinction. A theory could be true or false, right? But could be empirically adequate, whether it is true or false. Because this requirement is much less than truth overall, truth about what the unobservable world is like. It's just being right about the observable part of the world, in effect. Being right about what you get in your data models from your experiments. So, okay, I think I just said that. I could illustrate this by talking about some specific experiments, like one of my favorites here, but I won't do that unless you ask me to do that a bit in the discussion period. Okay? And then we can talk about how it works out in a specific case. All right, second polemical interlude. Is Bill here? No. Too bad. Okay. He has an argument in his recent book, which is a fabulous book, and I read it immediately, and I learned a lot from this tradition that comes down to us from logicism. But also in it, there is a critique of the semantic view. And the critique he gives is that, sorry, but even on your distinction, empirical adequacy and truth aren't distinguished after all. They collapse. That's what he argues, okay? And the argument he gives is a variant on one that he uses in a lot of places. Originally, it was Newman's objection to Russell, and it was a great contribution when Bill and Michael Friedman wrote an article about that and brought it out back to the philosopher of science to look at. It was also used by Putnam in his arguments against metaphysical realism, Putnam's paradox, as we call it, or modern theoretic argument. And Bill uses it against a number of claims. He says this form of argument works in a lot of places. And he thought that it would also show that in the semantic view, after all, we didn't find a tenable distinction between empirical adequacy and truth. So let me sort of quickly sketch the argument. I'm sure that quite a few of you are familiar with how Bill argues this. So he says, let's suppose that the theory is empirically adequate, defined as we do in the semantic view. Well, first of all, it will have to have a model that has the same size as the world, or as the domain that we are representing, right? So when he says the elements are in a one-one correspondence with things in the world, that doesn't say very much. It just says they have the same size. Okay? And then, of course, that model would also have to be right about the observable. So that with this correspondence between elements in the model and observable things has to be such that what is being attributed in the model has to be right, has to be true. Okay? Okay, so far so good. But then he says the correspondence with anything else in the world is not part of the story. So it could be anything. And now that gives us the leeway to just introduce the following trick, which Newman and Putnam had used too. When you want to know the extension of terms in the non-observable part, you just go to that correspondence and you define it from that. So it'll automatically fit. And now you have a model that is in one-one correspondence with the domain. The observable part is right, and all the theoretical assertions are true. So the theory is true, after all, completely. That's the argument, right? It's a beautiful form of argument, but there are several things wrong with it. Okay. Okay, that's the equations, right? First of all, the notion of truth that he is using here is incoherent all by itself. A scientific theory is not what the logician would call complete. There will be sentences that it does not assign truth value. Right? There will be questions to which it can't answer either yes or no. So that means that logically there will be at least two different extensions of that theory, perfectly consistent. In one, you get the answer yes, in the other one, you get the answer no. So in this one, that some particular sentence is true, and the other one is false. Now, if you use his notion of truth, then both the theories are true. But of course, now you have a true contradiction in nature. A is true and A is false, and that's not a good notion of truth, right? Okay, so this is not a good notion of truth to use. But, well, that's a quick way to stop the argument. But there's something much more important at stake here. It's about how, in this case, he is reading this semantic view in just the way that Halvorsen did. As having inherited from the logical positivist this view that the theoretical language is in itself unintelligible. That any interpretation of theoretical language is going to be okay. But that's not true, because the language in which the theory is presented, the way that scientists present the theory, is in natural language. Okay? So this assignment of extensions to predicates has to be right. It has to assign to the word electron the set of electrons. Now, maybe that set is empty. Who knows? Okay? But it has to assign the right set. And otherwise, it's not an admissible interpretation. So it's quite wrong to say that after you've covered the observable part, anything goes in how you connect the models with the world. That's just not true. Okay? It's not a model of the world if in the model the set of electrons is the set of blood bubbles. Okay? Okay. So I think that, again, like with Halvorsen, it's not so surprising that people would look at it that way. Because if all you say is the C view was rejected and the semantic view was put in place, then you haven't said how much of the old was kept. And of course, we were keeping the formal methods, that's very useful. But we were not keeping this conception of language that we saw as completely refuted by people like Feyerabend and Kuhn and Maxwell and Sellers and Hansen. Okay? That's my answer. Okay. All right. Well, now I come to the last part of the story. Right? So, Dick Hughes was very much involved in the semantic view. He was a student of Jeff Group, did his dissertation with Jeff. I was on his committee. Then we worked together on things in quantum logic and probability. And he wrote a book about quantum mechanics that he says this is within the semantic view. He was very much involved. He died very recently, sad to say. So in 1996, he wrote an article for Encyclopedia of, I think, something in physics, but something in applied physics, Encyclopedia of applied physics, something of that sort. in which he describes the semantic view. And he says that, well, now it's, 30, 40, whatever number of years old, and there have been developments, and he says there's an early development, which he discusses very briefly, but he thinks the central figure was Patrick Suppes. Okay. And he mentions that Suppes' student Joseph Sneed had developed in a very formal way and taken it to Germany and started the whole German structuralist movement there, right? Second stage, he identifies with this development of the treatment of scientific theories in terms of state spaces and that led to the development of quantum logic. So that one of the great applications, of course, and certainly for Rick Hughes himself, was this application of the foundations of quantum mechanics. But he says now there's a third approach, a third stage. He just classifies it as a new stage of the semantic view. And he starts describing it. Now, he mentions actually two forms of follow-up. One is one that begins with Cartwright and also Geary and Fred Suppes at the time, which says, shift the focus from the big theories, relativity, quantum mechanics, cosmology, shift it to local modeling of experiments and applications. So like, Nancy Cartwright presenting models of lasers, for example. Let's focus on that. That's a very different way of developing the view, focusing on that. And he says, the other thing is that representation was always an important term in presenting this view, but we have to start focusing on what exactly that is. What is scientific representation? What is representation by the model? Okay. I think that some distinctions he could have made, because actually it's quite different between when he mentions Cartwright and Geary. Cartwright does exactly what he says there. Geary, who started using the term model-based view, is doing something like that, but still on a much more abstract level than Nancy Cartwright did. But he starts discussing the hierarchy of models, from data models to more general to highly theoretical models, and talking about relations between models and phenomena of a much vaguer and indefinite sort through approximation and idealization. Also Paul Keller was involved in that. And I think you probably have to distinguish these two forms. And then the other one, the representationalist approach, well, that really started with Hughes himself just at that time. In the next year, he publishes an article called Models and Representation, which many people cite today as having started a whole series of papers on scientific representation, first by himself, then by Suarez, by Frigg, by many other people. Okay. Geary also was involved in that. And Hughes' account is very interesting. It really set the stage for whole new discussions. It was called the DDI account. The notation, as I said, you have to say what the model is of, first of all. Secondly, demonstration. The internal structure of the model allows inferences about the subject, and interpretation, which is what does the model represent the thing as, right? So the wave theory represents models of light, as a wave, and then internally in the model, you see all these connections between things like wavelength, frequency, velocity of transmission, and so on. And you can use these inferences to make inferences about the subject that it is of. It's a beautiful paper. He starts by analyzing modeling by Galileo, and then goes to contemporary examples. So I think that he's right that this was a new development. But this is already where sort of questions for me begin to happen. I mean, I said that the semantic approach is now 50 years old. I didn't imply that it has been alive all that time. Okay, maybe already in 1996, what we see is a replacement, several replacements, going in different directions. Certainly, Nancy Cartwright in 1983 begins by saying, she discusses semantic view, but then, no, that's not it. She is doing something new. So I don't think she would accept it as a new state of semantic view. At least she wouldn't like to use the term, right? Geary kept the term semantic view through most of the 80s, but at the end starts saying model-based view, right? So I think that at least as far as terminology is concerned, you already see some suggestion that there's a replacement going on rather than a development. So is this the end of the affair? So I want to make some speculative suggestions, but then I would like to definitely hear what different people think about what could be happening now or what could be in the wind, right? When I look at the current literature, it's hard for me to have any doubt that models will remain at the center stage of philosophy of science, everywhere in philosophy of science. Okay? I mean, that was a shift from theories to models that was the beginning of the semantic view, and I see it going on much more now than ever. So I think that this will remain focal, that's my guess. And that it's really important that we always keep in mind that when you discuss a model, you have to do it in two directions. Okay, the model is a model of the theory, right? Possibly a model of the theory plus many observing assumptions, and it is a model of a phenomenon. So the up direction and down direction use the same word "of" in both cases, right? If you only think about the models of a theory and leave out the other part, then you're just doing mathematics, special case of model theory. If you forget that the model is a model of a theory, the background theory that initiated the construction of the model, then you get Margaret Morrison's question in an article that she put in Philosophy of Science. Where have all the theories gone, right? You have to have both. Even if you work on one side, you have to keep the total framework in mind. So when I look at what happened with Nancy Cartwright's work, some, I was at a conference recently that was called the Conference on the Stanford School of Philosophy of Science, and when I was invited to it, and my first reaction was, well, they mean Patrick Suppes, right? And no, what the organizer meant was Nancy Cartwright and her students, okay? And he also didn't include later people like Michael Friedman and Tom Rickman and Helen Longino who were at Stanford. So it was a very specific reference. I do see this new movement of philosophy of science in practice as coming out of things that were advocated, at least in the beginning, by Nancy Cartwright. Right? That and the people in philosophy of science in practice are very evangelical. So maybe that's the way to the future, right? Then the people like Geary and Teller, they object so much to anything that ignores the imprecision in scientific modeling and application. They want to give lots of attention to vagueness, to the limits of idealization, to the use of approximation. And of course, there's a book by Batterman called The Devil's in the Details, right? That is an important direction, and maybe Paul Teller argues that you're losing sight of what is really crucial in science when you try to think of it in some sort of precise reconstruction. Right? Then there's this literature about representation, which started making connections also with computer simulation and so on. And then finally there's Halverson, who says he wants to go back to a really formal framework and using new mathematical tools like category theory to describe the structure of the space of models. And all of these things are tremendously interesting. I see connections with other aspects that are discussed in philosophy of science, like the philosophy of science in practice is connecting with technology, philosophy of technology, right? And with historical case studies. And the sort of thing that Beery and Teller are talking about make connections with fiction and literature and philosophy of language, where vagueness has been the topic. It was not the topic in philosophy of science before, but in philosophy of language. And representation, as I say, it connects to art and computer simulation and data visual display and data processing and so on, which has all kinds of interesting questions in it. So each of these things has promise, right? There may be other things I haven't mentioned, right, that I haven't even thought of. So I'd like to have your reactions on that.
Before we begin questions, I'd like to present Ross with the coveted Rotmanist and Western bag.
Present. Okay, thank you.
Thank you very much.
That's really great. Thank you.
I can try to manage a queue for you, because I imagine there are a number of questions. So, okay, Robert, you're first. Oh, and there's the microphone.
Doing feedback.
So you want to send the microphone as well, I guess.
Thanks very much for the overview. A couple of points. One is basically historical, I think. You said toward the beginning that it was a problem with the received view that it regarded the fundamental theoretical terms as uninterpreted.
Yeah.
That they should be interpreted literally in natural language. But then part of the inspiration for this whole movement was, as I'm sure you know, problems that arose in the 19th century about empirical claims whose interpretation still had to be figured out.
Yeah.
Like the claim, for example, that space is curved. That's not a claim that anyone would have been able to understand until philosophers worked on the problem of how these spaces, which have been studied abstractly, could possibly be in the space we live in.
Well, you know, they understood it well enough to understood things like Gauss's work to show how you could make internal measurements to see the curvature of the space. They understood it. But then, of course, all kinds of questions arose. So, you know, as I said, the fact that you understand the language at a sort of initial level doesn't mean that there's no role for interpretation. In fact, every puzzle that you have is going to ask, hey, how can we interpret this more fully so as to, you know, get answers to these puzzling questions, right? If you begin by saying, oh, well, we can find out whether the curvature is zero or positive, we make some measurements on distances between three stars. But what about measurement and distance, and right?
Right, but that's really my point. There were serious questions about how to think of such an abstract structure as being possibly applicable to his theory.
Yeah.
And one thing, I thought that your characterization of what's wrong with the use of the Newman argument was a little bit beside the point, because it leads to an incoherent theory of truth.
Yeah.
But on the other hand, it isn't an attempt to defend a theory of truth. It's an attempt to show that the use of isomorphism as a way of describing the link between the theory and the world trivializes the notion of the truth of a theory. And by the same token, it trivializes the notion of a theory saving the phenomena, right? Because you can always find an isomorphism.
Yeah. Well, you know, of course, my view is that it doesn't trivialize because you're talking about inadmissible interpretations, right? You're forgetting that you already understand the language in which it is presented. Now, maybe you understand it only up to a certain point, but that understanding has to be respected. Right? You know, the straightforward claim that Bill makes is empirical adequacy collapses into truth. That's what Richard Boyd and Michael Gardner were saying. They were saying that if you really apply the criterion, you end up with just true theories that are empirically adequate. Now, that would be a terrific result if the word true means what we mean by truth. It's not going to be a terrific result if the notion of truth that's applied is incoherent already, right? So that, I mean, I think that is one way, because look, you say that the theory has a model that fits the world in that sense, right? That means that under some interpretation the theory is true. Well, who can infer from under some interpretation is true to the statement it is true? It's not a good inference. Right?
Well, it's not meant to be that sort of inference, at least in the case of Newman and Putnam and the novelists too, I think. But it's meant to show that if all you have to say about the relation between the structure and reality, or the structure and the appearances, is that there are isomorphisms, then you really haven't said anything.
Yeah, that's absolutely right. Of course, that's absolutely right.
Which this is just a question about what your reason was. I mean, my impression was that part of what you've been trying to do recently is to sort of fill in this gap with your discussion of exactly what's meant by an admissible representation.
Yeah, that has to be, sure, it has to be articulated properly, of course. And I also don't think that interpretation, it's like with the interpretation of a novel. It's not like the text of the novel and the structure of our language will dictate a unique interpretation of the novel, right? But that doesn't go to the sort of extremes that are needed for the Newman argument to get rid of the semantic view. I mean, the fact that there are open questions about what's happening in Paradise Lost, doesn't mean that Paradise Lost couldn't be true, right? Okay.
Carrie.
Thank you very much for that. I guess this is just a sort of addendum.
I'm sorry, I can't quite hear.
Yeah, sorry. Kind of an addendum to the previous question. So, on the Demopoulos point, so there seems to be really a lot of confusion about this. This idea that the structures that are written down, the little angle brackets, right, when you write down the model of the theory, that they're supposed to be interpreted, but they're interpreted as they're physically interpreted from the get-go, right? So you kind of suggested that this is maybe down to a lack of appreciation at that point, down to some kind of hangover of the received view.
Yes.
But I mean, it seems so. Perhaps, I mean, do you think that also, because it is a really widespread kind of misunderstanding, but it is a misunderstanding. Also, Suffolk saying that talking about this semantic approach and talking about it being cast in the language of science as mathematics, not meta-mathematics, right? Which makes it sound like what we're looking at is something that is not physically interpreted, or also maybe because of for whatever reason, the fact that structuralists sort of grabbed onto the semantic approach, given that the Newman objection was, of course, sort of originally framed in that context.
Yeah, well, you see, this is why we thought of Sufi's approach as too extreme, because there's so many questions about the language of science that are philosophically important. And when he says, let's just look at the set theoretic structures, we're saying, well, we have to do a bit more than that. The structuralism, if it's not presented properly, it trivializes very quickly, right? But I think that the more sophisticated structuralists, like Stephen French and James Leyden, don't really fall into those traps. Mind you, the kind of structuralism that I would subscribe to is not theirs, for sure, right? But I think that there is something that is right at the core of structuralism, which is the models that science presents us with are mathematical structures, okay? And mathematical structures do not distinguish beyond isomorphism. You don't say have two distinct mathematical structures and they're isomorphic in every respect. That doesn't make sense, right? But the model, scientific model, although it is a mathematical structure, that's not the end of the matter. I mean, the Mona Lisa is a painted piece of wood. It's true, that painted piece of wood is the Mona Lisa. But boy, the general theory about paint and wood doesn't throw much light on what the Mona Lisa is. Okay? And the same as scientific models. The fact that it is a mathematical structure doesn't by itself throw enough light on what is a scientific model.
Hi, thanks. I am continuing on this thread, I think. I hope it's a useful one for you.
Okay.
So, given your background in philosophy of language, I was surprised at your appeals to natural language as being the language of science. And it's pretty clear that what it is you don't mean by that. So for two reasons. One is, as has been stressed from Frege through Austin and Searle through Chomsky, natural language sentences don't have truth conditions. They're not true or false, either to Coeur or even relative to a small number of parameters, and natural language predicates don't have extensions the way you would want. So natural language sentences lack one of the key semantic features.
Oh yeah, you know, I don't agree with any of that. Okay?
Oh, you don't believe me? Well, maybe that answers that is a problem, though. Since the empirical evidence in favor of those conclusions is absolutely overwhelming.
You know, I have to see exactly what you have in mind by that, because I'm sure there's all kinds of ordinary English statements that you're willing to make at the moment that you will all agree are true.
Oh yeah, there's statements I can make that are true.
Oh yes. Oh, and then what?
But it doesn't follow that sentences of natural language have truth conditions.
Independent of the context of utterance.
Well, and even once you specify a limited number of parameters because of vagueness and other kinds of context sensitivity. So it's one thing to say that people make true statements with sentences, absolutely. Quite another to say that sentences are the bearers of truth conditions and satisfaction conditions, and the predicates have extensions.
Okay,
the other thing is that it seems that natural language sentences have lots of pragmatic properties that we don't want scientific sentences to have, like illocutionary force and level of politeness and tone, and the difference between vomit and barf and intercourse and fuck, right? Really don't seem to be things that we want. So to repeat where I started off, in what sense are you willing to appeal to natural language as doing the kind of work for you and getting you?
Well, you see, I think that what you are talking about are difficulties with scientific modeling of natural language. The kind of scientific modeling that linguists and formal semanticists want to do. There are lots of difficulties with scientific modeling of natural language. That doesn't mean that the natural language in which you and I discourse is not understood or is unintelligible, you see? And that's what I'm relying on. And when the scientist presents a theory, like for instance the theory of evolution, right? We all understand it, okay? The fact that, it's very difficult to understand how cats always land on their feet. Okay? These are difficulties with the physics of cat movement. There are no difficulties with the cat. And the same with natural language. I think that, when it comes to formal modeling of language, I like Haskell v. Curry much better than Tarski. And Curry has the point of view that the logician, too, is always speaking at this one level in natural language. He's never speaking in what Carnot calls a meta-language. Rather, he will make a model of some part of language, and then maybe make a model of that, which will be his meta-model, and so on. But still, that's what he's talking about in natural language. And this is the point of view that I favor.
I've got two questions. I'll start with the second, which is related to what we've been discussing, the human objection. I couldn't see the force of the reply. in the following sense. We know apparently that if you've got a consistent theory, by the Scholar-Morgenheim theorem, you can show that you've got the model of cardinalities and the model of natural numbers. Now, you don't want to deny that, of course.
Right.
But you would like to say, I guess, that this is not the right approach to scientific theory? Because if it is the right approach to scientific theory, that means if you can actually say that you can find some construction, you can find a model in the world, or some arrangement in the world, or some rearrangement of things in the world, or some arrangement of natural numbers. You can actually run the Newman objection against the gap between empirical adequacy and truth by showing you can actually perform, or you could perform with this math. You can actually find this model which will satisfy the theory if it is empirically adequate. And because you might say, no, I don't like this move going to scientific theories, you seem to introduce intention. So the intended meaning of the theory is electrons, not anything that but how can you say that? Not to anyone. I mean, you need somehow to say that there are some independent ways to say what there are in the world as opposed to getting the things right in the world. And I'm not sure how this can be done.
You know, I see the Newman objection as an objection to show the inadequacy of certain kinds of formal models of language, okay, and of theories. And it's a very good objection, for instance, when Russell writes the analysis of matter, and he says that the only objective features are the ones that can be defined by purely logical definitions using only variables and not substantive terms. Well, he's wrong. I mean, then you don't have a non-trivial scientific theory anymore, okay? And, and similarly for the other applications of the argument, they show the inadequacy of certain kinds of formal treatment. If you take the language of the theory of evolution, and you formalize it in the first order language, and then you start looking only at the models that the logician allows for the set of sentences that you've isolated in that first order language, you will get all kinds of strange models, okay? And you won't have to look, and if that's all you're looking at, you don't have a notion of truth, really.
But it's supposed to be a philosophical argument. It doesn't say about models of populations and ethics. It says let's think of evolutionary theory as a theory. Okay? It presents the way the world is. Let's say that it's empirically adequate.
No,
we know it's not. We know we'll never be able to say that it is. But let's imagine that it's empirically adequate. Does it make sense to raise the next question? Is it thereby false? And that's apparently a principled argument, philosophical argument with mathematical logical elements to show that this gap is not there. So by saying that this does not model the way biologists use evolutionary models, I don't think it targets the substance of the argument.
If you give a formalization of the theory in the way that logical positivist does, right, then you give an incomplete picture of what the scientific theory is like. Then if you treat that as a complete picture, of course you run into trouble.
No, don't treat that as a complete picture. I treat that as a philosophical idealization on the basis of which I can now raise the question, does it make sense to distinguish between empirical adequacy and truth? And probably I'm wrong about that, and Bill is wrong and other people are wrong. But it's a philosophical question. And this actually brings to my first question. So what is the big advantage of the semantic view theory over the received view? That it better corresponds to the actual practice and use of theories in science? That's the big advantage.
Yes.
Is that the only advantage, or is it?
Well, it helped us to make sense of the logic approach to information and quantum mechanics. It helps us to make sense of the relation between measurement results and theoretical models. It helps us to resist the kind of trivialities you get into with this overly logical formalization of theories, which logical positivists thought would give you the whole story, because it allows us to it brings us to study the representation relations that are really involved, which means relations again between data models and theoretical models. So yes, these are all advantages that have to do with getting a closer look at science, at the way science is done, both in experimentation and in modeling, and in the experimental side of modeling, and in the development of theories. So yeah, I claim those advantages, yeah. I think that the Newman argument, it's even difficult to state if you go outside the received view. It is really wedded to this idea that there's part of the theory that's connected directly with the observations, and a part that has to get its meaning indirectly. And that's just the wrong, that is something that went out with Kuhn and Feyerabend and Hansen, etc. And I don't see why it should be. So, look, Dildomopoulos doesn't have this view of scientific language. He was a student of Grover Maxwell. So he clearly doesn't have this view. But he's attributing it to the people who use the semantic view. Yes.
I think this will actually be our final question from Carl.
Okay. Can you go back to the slide that had Cartwright and Geary and Suarez and all these people on the latest development?
Let's see. Here's overview.
No, it would be 30.
The next one?
Later.
The next one.
Yeah.
That one?
So I was getting confused in a certain way towards the end about what are all these people doing?
Yeah.
And
Okay.
and I reflected. So what was the question that we were starting to with that the received view was one answer to, and the semantic view was a different answer to.
Right.
And I guess it was, what's the nature of a scientific theory?
Yes. Yeah.
And I just want to make a suggestion that starting in 1989 or so, Nancy Cartwright's not answering that question anymore. She's not interested in that. And so looking at her followers and her work is going to not
Maybe
be so
take
helpful.
us out, definitely outside. Yeah.
And
That doesn't surprise me. I mean, I think that Nancy herself would certainly resist the idea, would resist Hughes classifying her as a development of the semantic view. Yes.
And I'm sympathetic with it because you can see a pattern emerging over the history, which is people try to come up with one big global theory of what scientific theories are.
Mm-hmm.
But science is rich and diverse, ideally as rich and diverse as the whole world is, because science is trying to find out about the whole world. And so if we keep going through this cycle of trying to come up with tidy, interesting, non-trivial accounts of what a scientific theory is, well, we're going to have lots of counterexamples and problems.
Well, there are scientific theories, right? I mean, even if in many places the scientists' work is with particular families of models. And so, one thing that I became a bit more acquainted with is fluid mechanics in the past 10 years or so. And talking with physicists who work in that, I can see that their whole attention is on specific sorts of models, okay? But they're very conscious that they get their equations from classical mechanics. And they often talk about justifying specific equations, and by that they mean connecting it with the much more general equations that the theory gives you. So it's not like the background of theories is going to disappear there. Of course, it may be very valuable to really focus on, for instance, how in a particular lab, a series of models is developed. One is developed, it has problems, it is replaced by another one. Models are used to construct other models. It's a wonderful thing to be thinking about, and I think philosophers of science are very right to start thinking about things like that. But I don't think that scientific theories simply disappear, or that the question, what is a theory or what is a model, are going to disappear. You probably know Margaret Morrison's paper, where have all the theories gone, right? So this is a critique of that kind of approach.
Okay, so I'm sorry that I have to cut discussion off here. There's actually another group who's coming in to use the room. So let's thank Professor Lombardi. And I do have to ask you to